Hello everyone, I'm Erin from WebNazar, your digital lens on everything trending. Today, we're diving into another important story, idea, or innovation shaping our world.
Over the last few years, the rollout of 5G achieved something massive. It successfully linked billions of mobile devices together, giving us the bandwidth to stream, video chat, and transfer high-speed data from almost anywhere on Earth. Back in 2010, global mobile traffic hovered around 7.4 exabytes per month. By 2030, that number is projected to hit over 5,000 exabytes. The sheer volume of data is about to place an enormous strain on our existing systems. The problem is that current cellular networks operate as blind data pipes. They are highly efficient at pushing bits from point A to point B, but they have absolutely no awareness of the physical environment they are passing through. If we want to deploy millions of autonomous drones and factory robots, they will require millisecond-level interactions to avoid collisions. A network that cannot see its surroundings simply cannot manage that kind of physical traffic safely. To survive the demands of the next decade, the telecom industry has to do something completely different. The global infrastructure has to evolve from a passive communication tool into an active, real-time radar system, mapping its surroundings continuously. Researchers are currently looking at entirely new frequency bands for 6G, specifically the terahertz and millimeter wave bands. We are talking about incredibly high frequencies, ranging from 100 gigahertz all the way up to 3 terahertz. Because these waves are densely packed, they can carry an enormous amount of information. In theory, these bands could push wireless data rates to a blistering 1 terabit per second. This animation illustrates the defining physical challenge with terahertz waves. While a low-frequency wave easily passes straight through a wall, a high-frequency terahertz wave is so fragile that it will bounce right off obstacles like trees, buildings, or even human bodies. Engineers are taking that supposed failure and using it as a feature. Instead of trying to force the signal through, 6G systems will measure those reflected waves to gather highly detailed information about the physical environment. By reading the echoes of these high frequencies, the network uses the exact obstacles that used to block signals to map out and see the world around it. This photo shows a laboratory setup testing a concept called Integrated Sensing and Communication, or ISAC. This is the process where a single radio wave acts as both a data carrier and a radar pulse at the exact same time. During a scan, a 6G beam bounces off a person walking through the room. Calculating the timing and angle of the reflection lets the network pinpoint their exact physical coordinates. This visual output reveals what the network actually sees. You can clearly identify the moving target, isolated here as the green arc labeled H, standing out against the background inside the radar's beam cone. This chart plots the target range over a 10-second window, showing how the person's distance shifts in real time. Right below, the target's speed is tracked from that exact same signal, measuring movement down to a few millimeters per second. Indoor environments are messy. This heat map shows the raw, unfiltered data, full of intense reflections from stationary objects like metal cabinets and support pillars. The network algorithms have to filter out this static noise, a process known as clutter removal. Once that filter is applied, we get this much cleaner visualization. The stationary clutter is completely gone, leaving only the moving human target visible to the tracking software. ISAC effectively turns every cell tower and router into a spatial sensor, tracking the physical dimensions of the world with incredible precision without a single optical camera. Tracking thousands of moving objects across millions of radar signals creates a staggering mathematical burden. Human-coded protocols are too rigid to process this volume of environmental data on the fly. That requires an AI-native air interface. In this system, machine learning algorithms take over, actively designing and optimizing the radio connections in real time. This graphic illustrates the concept of AI RAN. By fusing connectivity and compute power, the network uses artificial intelligence to instantly allocate spectrum and adapt to whatever hardware or physical obstacles are in the environment. To keep everything running with ultra-low latency, the heavy lifting of processing this radar data is handled right at the edge of the network, locally at the base station itself. By weaving machine learning into its architecture, 6G is the first wireless generation built from the ground up to be operated by artificial intelligence. When you combine the massive bandwidth of terahertz frequencies, the radar-like tracking of ISAC, and the real-time processing of AI RAN, something entirely new emerges. Because the network constantly sees and tracks every moving object in its environment, it can instantly translate that physical data into a perfect 3D digital replica. This is known as a digital twin. It is a live virtual simulation of a physical system, like an entire smart city grid or a manufacturing plant, that exists completely in the digital space. By running analytics on this live simulation, operators can optimize resources, monitor complex industrial automation, and accurately predict exactly when a machine needs maintenance before it actually breaks down. For individual users, this creates the foundation for true extended reality, or XR. When the network perfectly understands the dimensions of a room, virtual and augmented elements can seamlessly interact with the physical tables, walls, and people around them. A system capable of mapping, tracking, and simulating its environment in real time serves a completely different purpose than a 5G connection. It is an entirely new layer of infrastructure designed to merge the physical and digital worlds.